All right, so this is the second lesson in 1D kinematics. And in this lesson, we're going to deal with solving with the big five equations. So we're going to look at five equations that relate displacement, velocity, acceleration, and time. So one of these equations you have already seen. Equation number 5, you have already looked at. That's not a new equation. Now these five equations, we could derive and rearrange to come up with them. But we don't have the time to do that. In some courses I've had, they have requested that we do that, but we simply don't have the time, so we're going to leave that out. But these five equations look kind of ugly, but they really help us out because sometimes you know your starting velocity, you maybe know your finished velocity, but you don't know the distance over which, or the displacement over which that movement occurred. So if that's the case, we can look through this list and you'll notice there's pieces that are missing in each of them. So equation 1 uses final velocity, initial velocity, acceleration, and time, but it does not include displacement. So if you don't know the distance over which something has occurred, we can still calculate velocity, acceleration, or time. We can calculate one of the other missing pieces. Sometimes we don't know the ending velocity, but maybe we know the beginning velocity and we know the acceleration. And in that case, we would use equation 2. We don't have a final velocity. Equation 3 is helpful when you don't know how long something took place over. Equation 4, I use that one if I don't know what the acceleration is. Once you find one of the missing pieces here, then you're able to find the acceleration. And then equation 5 is the one we've worked with so far. And you'll notice for the equations that we used last time, we didn't have to worry about distance, or more specifically, I should adjust the wording here and put displacement. I'll edit that after. So how do you use these equations to solve? Now these equations are the more complex problem solving from a math perspective. Maybe not as complex from a theoretical perspective, but from a math perspective, people sometimes get stuck with them. So these are my strategies. First of all, read and diagram. If you can read and draw a picture, it helps just to be able to visualize it. Secondly, list the knowns. So make a list of the 5 key variables and fill in the quantities that you know. And that's what we're going to model. I'm going to show you how I would calculate each of them. Then identify what's the unknown. So which one do you need to solve for? That's the one that you're going to just leave as a letter. Find an equation. So the equation should only use the known variables and then include just one unknown. There shouldn't be more than one thing that you don't know in an equation. And then we're going to substitute into the equation and solve. So those kind of 5 steps, they're really straightforward, but they are really helpful if you follow them. So I've got 4 example questions for you to do. And I'm going to do them with you, and we're going to be able to jump back and forth between the formula sheet, so hopefully that will help us out. I like having the formulas on the same screen, but that's just not feasible. A wrench is dropped by a technician on a wind turbine. It hits the ground 3.5 seconds later. From what height was the wrench dropped? So in this question, we're going to fill in the information that we know. This one is a little bit of a tricky question because there's some hidden information. So we know time is 3.5 seconds. So we've used this piece. We want to know, it says from what height was the wrench dropped. So that's going to be our displacement. So we need to find that, but it feels like there's nothing else. And we need to have at least 2 other pieces of information. So if you drop something just before it leaves your hand, while it's still in your hand, it does not have a velocity. So anytime something is dropped, we can say velocity at the beginning equals 0 meters per second. So there's one of our hidden pieces. If something is dropped, we also know acceleration is caused by, I don't know why that shows up all the time. Acceleration is caused by gravity, which is negative 9.81. That's meters per second squared. All right, so there's 2 hidden pieces of information there, just put in that word dropped. And I don't expect you to know that right at the beginning. We're going to deal a lot with things that are being dropped or things moving through the air. when we get to our next lesson. So we know that the final velocity we don't know, but we know what right at the beginning, when it's just dropped, velocity is equal to 0. As it rockets down towards the ground, falls towards the ground, the speed or the velocity is going to increase. So that makes sense. It's going to start at 0. And the acceleration, when it drops, is caused by gravity. Gravity pulls downward, so it's going to be negative 9.81 meters per second squared. So there's some extra hidden info in that question that's not told, but now you'll be able to watch for it. We don't worry about it too much today, but we will keep going with that. So you'll notice there's one piece here, velocity, final. We don't know it and we don't care about it, so we're going to get rid of it. So we've listed our pieces, we've identified what it is we need to solve for. Now we need to find an equation. So we need an equation that does not use final velocity, but has everything else. So looking at our formula sheet, this one has final velocity, this one does not. I have distance, I know the starting velocity, I know the time, I know the acceleration. So we're going to use equation number 2. Might be helpful to print this off and just have this on as a quick reference. So equation number 2 is distance is equal to initial velocity times time plus 1/2 AT squared. Substitute in the information that you know. So we want to find distance. We're going to leave that as d is equal to 0 meters per second. I put brackets around things only because it helps keep the units together. It's just more for visual for me when I have units attached to things. 3.5 seconds plus half. Acceleration is negative 9.81 meters per second squared. That negative sign is really important. And then our time is 3.5 seconds. We know this term is just going to be a 0. I don't even have to put that one in the calculator. So we get distance is equal to, plugging all of this piece in the calculator, I get negative 17.2 meters. Looking up here, I have 2 sig figs, so we're going to round that up to negative 17 meters. So therefore, it falls 17 meters. Okay, these 3 little dots just mean therefore. Not too complicated, especially nice that we didn't have to do any rearranging. Our next question, we have a jet traveling 65 meters per second, accelerates at 25 meters per second squared for 8 seconds. What is its final velocity? So we're looking for final velocity, so that's what we want. It starts out traveling at 65 meters per second. Acceleration we know, so it's speeding up at 25 meters per second squared for a time of 8.00 seconds. We don't know how far and we don't care about how far, so we can leave that out. I need an equation that does not include distance or does not include displacement, but has everything else. So let's return to the formula sheet. Looking at our formula sheet, I see there's no D here and there's no D in 5. Actually, equation 1 and equation 5 are really the same equation. I probably didn't need to put them up twice, but whatever. Sometimes the brain doesn't always do what you want it to. So we want to use something, so we're going to let's use equation 1. Okay. We don't have displacement and we don't need to know it, so we'll use that one. So we'll go back to example 2 here. So velocity is equal to initial velocity plus AT. So we don't know what this is. We're looking for it, so we'll leave it as B is equal to 65 plus 25 times 8. Everything was in meters and seconds. You could throw your units in if you want. I'll confess, sometimes I leave them out just for the sake of easier to write things. And we get 265 meters per second for a velocity. We'll notice here we have 2 sig figs everywhere. So if I round to 2 sig figs, that would take me to 270. 2 sig figs would be rounding to the 10th place. So 270, meters per second. Now I just do that because sometimes you'll have questions and you'll go, it says 265, but why does, I got 265, but why does the book say 270? And in some cases, it's just a matter of rounding, just sig figs. So that can help you out there. So that's our final velocity. Let's look at the next question. Example 3. What distance is covered while a car accelerates from 66 meters per second to 44 meters per second during an 11.4 second period? So again, we're going to fill out our pieces. So what distance is what I'm looking for, and fill in our knowns. So we're starting at 66. I'm going to 44. And it's 11.4 seconds. Now I don't have the acceleration and I don't need it, and that's okay. Quick question. Would this have a if we were to calculate acceleration, would this be a positive acceleration or a negative acceleration? We're going from 66 meters per second to 44. If you predicted a negative acceleration, it's actually slowing, which would be a negative acceleration. We are still allowed to use the word acceleration for that. All right. So now let's plug and find an equation. So we need an equation that has distance, but does not use an acceleration. So if we look through, this one does not have distance, it has acceleration. This one has acceleration, this one has acceleration. This one does not have acceleration, so we can use equation 4. So let's use equation 4. Distance is equal to 1/2 of 66 plus, I'm going to actually write, let me just erase here. I'm going to write the equation out first. So distance is equal to 1/2 VI plus VF, V plus V. Oh dear, I'm getting myself all kinds of trouble here. There we are. Sometimes you discover features you didn't know existed. All right, 1/2 V0 plus V times T. Okay, 66 plus 44 times our time of 11.4. Notice everything is in meters and seconds, so we're good with our units. Plugging all of that into your calculator, you'll find you get a distance, make sure you follow order of operations, of 627 meters. Now again, let's do our sig fig check. 3 sig figs, 2 sig figs. So we would round that to 630 meters is the distance. And that little squiggle just means approximately equal to 630 meters is how far the car would travel during that period. And one final question I'm going to do with you. This one comes from a great question from the physics book. I've rearranged it a little bit to use the equations that we want. So this is actually a 2-step question. We can see that because we've got 2 questions in a question. An arresting device on an aircraft stops a plane over a distance of 55 meters. The average plane deceleration is 49 meters per second squared. What is the average initial speed of the plane? Apparently I can't write when I write questions down, I leave out words. My apologies. And then we want to know what is the average amount of time to stop the plane. So we've got, first of all, what's the average initial speed of the plane? So we're going to fill in some information and we're going to do the calculation. So it stops a plane. Stops tells me that the velocity final is 0 meters per second. So we can plug that in. Distance is 55 meters. And it decelerates. So this means this has to be negative. So acceleration is negative 49 meters per second squared. And what's the average initial speed? This is what I'm looking for. So I don't have time. I do want time, but I want the time later. So we'll just begin with these 4 pieces for now. Looking at the formula sheet, I want an equation that does not have time. You'll notice equation 3 does not have time, but it has final velocity, acceleration, and distance. So we'll use that equation. V squared is equal to initial velocity squared plus 2AD. Substituting in, velocity squared is equal to, oh, let's just erase here, missed a piece. So we have initial velocity is 0 meters per second is equal to our initial velocity, which we want to find out, plus 2. Acceleration is equal to negative 49 meters per second squared times distance, which is 55 meters. Now, I'm not going to bother with unit analysis. We know if we're putting meters and seconds in everywhere, we need to get meters and seconds out in our velocity. So let's solve this. We'll get 0 is equal to velocity plus, adding these pieces together, we will get a negative 5390. Okay, we need to get initial velocity alone. So what we're going to do is we're going to turn this to a 0. So we're going to add 5390 to this side because that'll cancel out the negative. And we're going to do the same thing over here. So we get 5390 is equal to, left off squared sign, I see, initial velocity squared, take the square root of both sides, and initial velocity is equal to 73 meters per second. 2 sig figs because we have 2 sig figs everywhere else. So that's our initial velocity. Then the question says, well, how long does it take? So now that we have this, we can pretty well pick any equation that we want. And if we go to our formula sheet, well, which equation looks easiest for calculating? We can use equation 1, and we can use equation 5, which is just a rearranged version of equation 1, doesn't matter which. You can use any equation at all in order to figure out the time, except for equation 3, that won't work. So let's use we'll use equation 1. So equation 1, to find time, velocity equals v naught plus at. Plugging our information in, we know 0 is equal to 73 plus negative 49 times time. We want to move the 73, so we're going to subtract it from both sides. So negative 73 is equal to negative 49 times time, divide by negative 49. Negative 73 divided by negative 49 gives us time equal to 1.5 seconds. So pretty straightforward. So that would be B, and we'll call this one A, just for the sake of putting them both into one. It's not quite enough room on a slide to squeeze 2 questions in, especially if I'm not writing super tidy. But hopefully that gives you the information and helps you understand. Now there are some practice questions that are in the notes that I've posted, and I'm going to post a video solution for those because I know some of you may struggle with rearranging those questions. So I'll post a video solution to kind of walk through how I rearrange those questions, because you will need to know how to do some rearranging. We haven't had a lot of rearranging practice in these questions.